we look at the duals of the various optimality problems that we have seen, optimum experiment design problems that we have seen, and then try to interpret them, interpret their meaning and the differences between them. So we will only look at E-optimality, and just I'll leave the others for you to work out. So the E-optimality problem, if you remember, was that 1 over T, A lambda is more positive definite than T times identity, and then 1 transpose lambda equal to 1, and lambda is greater than equal to 0. This problem can be written as an equivalent problem. So the equivalent problem would be minimize minus t. So instead of 1 by t, I minimize minus t, and then a lambda minus t times identity is PSD, and then the other two constraints remain the same. So then let us associate dual variable z with these two constraints, and then dual variable nu with these two constraints, and we'll keep this implicit, lambda greater than or equal to 0 implicit. So let us write down the Lagrangian. So the Lagrangian, which the primal variables are lambda and t, so Lagrangian is a function of lambda and t, and then z and nu are the dual variables. So the Lagrangian becomes minus t, and then we have minus trace of z times a of lambda minus t times identity, that is coming from the first inequality, and then plus nu times summation of lambda I minus 1. Right, so that is the Lagrangian. Let us now group this Lagrangian so as to separate out lambda i's and t's, which are the primal variables. So this can be written as t times trace of z minus 1 plus summation of lambda I nu minus trace of z times ai. Remember that a of lambda was summation of ai lambda I minus nu. So that's our separation, and then it is straightforward to minimize these with respect to t and lambda respectively. So we would obtain the dual problem. So the dual problem becomes maximize minus nu subject to constraint trace of z equal to 1, which is coming from this part, and then trace of z ai. Remember that lambda i's are greater than equal to 0. So the minimum of this part with respect, while assuming that lambda i's are greater than equal to 0, would occur when this term is also positive, because if this was negative, then the minimum would go to minus infinity. So this has to be positive, or in other words, trace of z ai is less than equal to nu, and this should hold for all I from 1 to k. And then finally we have that z is PSD. So these are our constraints. Now we can simplify this problem by eliminating nu. So basically this is just what we can do is do a change of variable. So what we can do is set w equal to z by nu. First observe that z is PSD, so therefore trace of z ai, which is basically ai transpose z ai. Remember that ai, capital AI was ai transpose. So this is ai transpose z ai is always greater than or equal to 0, because since z is PSD. So this is definition of positive semi-definite matrix. So this implies that because this quantity is always greater than or equal to 0, it implies that nu is always greater than or equal to 0, right? Because nu is greater than this as per the constraints. So therefore, if we substitute w equal to z by nu, then we can see that trace of w is equal to trace of z by nu, which is equal to 1 by nu, and then the constraint z is greater than or equal to nu translates to w is greater than or equal to 0, because nu is always non-negative. So therefore we can write the problem as instead of maximization of minus nu, we can instead maximize 1 over trace of w, or we could say we could maximize trace of w. So we could say that we could maximize trace of w, and subject to constraint, trace of w times ai is less than equal to 1. So this constraint becomes trace of w ai less than equal to 1, or we can write it as ai transpose w ai is less than equal to 1, right? And w is PSD. So this is the simplified version of the dual of E-optimal problem, right? Actually all three you can analyze and find their duals, and you would find that for A-optimal case the only thing that is difference is that these two constraints remain same, and then the objective function becomes max of trace of square root of w. And for D-optimal case we actually get max of log det of w, right? And the constraints remain same. So please verify this. This is actually problem 5.10 in Boyd's book. So let us summarize our result. Let us summarize all three things that we have seen so far. Just let me remind you that A lambda is summation of lambda I ai transpose, and the I indexes the locations, if you remember, and we had the D-optimal, and then we had A-optimal, and then we had E-optimal. So the primal formulations were minimize log determinant of A lambda inverse, and in the subject to constraints 1 transpose lambda equal to 1 and lambda is greater than or equal to 0. In the A-optimal case, the objective was minimize trace of A lambda inverse, again 1 transpose lambda equal to 1, lambda greater than or equal to 0, and in the E-optimal the objective was minimize lambda max of A lambda inverse, right? So everything is in terms of A lambda inverse. I have not written them in the standard SDP form. They are in the basic objectives that we have motivated, and let us also write down their duals. So in this case the dual was maximize log determinant of w subject to ai transpose w ai less than equal to 1 for all I, and w positive semi-definite. In the A-optimal case, the objective is maximize trace of square root of w, and you could say square of the whole thing, ai transpose w ai less than equal to 1, w PSD. And then finally in the E-optimal case, we have already derived it. It is maximize trace of w, and again same constraints, ai transpose w ai less than equal to 1 and w positive semi-definite. So these are the three formulations that we have seen so far: A-optimal, E-optimal and the D-optimal case, and we have found the three duals corresponding to each of them. Now what does the dual problem remind you of? If you remember, this is very similar. ai transpose w ai, this kind of constraint that this is less than equal to 1, is very similar to the quadratic discrimination problem that we have seen. In fact, there are no points outside. What we are saying here is that if I denote some points by ai, so ai are some points from 1 to k which are given to us, this problem or this problem or this problem basically involves finding an ellipsoid, so finding ellipsoid that encloses AI, right? So all the points AI from 1 to k are given to us, and we are interested in finding an ellipsoid that encloses these points, and the objectives are different. But we are basically interested in finding an ellipsoid that encloses these points, right? So the optimum experiment design problem in the dual domain basically involves finding an ellipsoid that encloses those points. There's one more point that you can observe from here. So suppose that I associate some dual variable with these constraints. Actually, that dual variable will be exactly lambda I, right? And what we will obtain from here, let's say, complementary slackness. So what does complementary slackness mean? Complementary slackness says that lambda I times AI transpose W AI minus 1 is equal to 0. So complementary slackness was one of the KKT conditions. So this means that either lambda I is equal to 0 or AI transpose W AI is equal to 1. So what does that mean? What does it mean for AI transpose W AI to be equal to 1? It means that the point AI is on the boundary. And what does lambda I equal to 0 mean? Lambda I equal to 0 means that no measurement, because remember, lambda I was mi by m. Mi was the number of measurements. So lambda equal to 0 means that there is no measurement at location I. So either you don't make any measurement at location I, or the point AI would be at the boundary of the ellipsoid. Now this is interesting, because if you think of AI as some arbitrary points, the ellipsoid that encloses them will obviously not touch all those points. The boundary points will be very few. And essentially this optimum experiment design problem is telling us that you only make measurements at points which are at the boundary of this ellipsoid. You don't need to make measurements at all the points that are strictly inside the ellipsoid, and you only need to make measurements that are at the boundary of the ellipsoid. So that's another interesting facet of this problem, which is revealed by analyzing the dual of the problem. Right, so we are measuring, let me just write it, so measuring only from sensors that are such that AI lies on the boundary of enclosing ellipsoid. So we need to find an enclosing ellipsoid, but once we have found an enclosing ellipsoid, then all we need to do is find the AIs that are on the boundary and measure only there. In fact, let us recall the ellipsoid. If you recall the ellipsoid, so equation of ellipsoid was x transpose A inverse x equal to 1, right? If you recall, ellipsoid equation is this, and eigenvalue of this matrix A, which is telling us the equation, is basically Ri square. It is the radius of the semi-axis. So the direction in which we are taking the radius is specified by the corresponding eigenvalue and the eigenvector, and the eigenvalue is the square of the radius, right? So in that sense, you can actually verify that the determinant of W corresponds to 1 by volume of ellipsoid. It corresponds to the 1 by volume of ellipsoid, right? And likewise, basically trace of square root of W corresponds to maximizing summation of 1 by Ri, right? Corresponds to maximizing summation of 1 by Ri. If you take the trace of square, then it corresponds to maximizing summation of 1 by Ri square, right? So these are the different metrics. In one case, we are maximizing the 1 by volume of ellipsoid, or in other words, we are finding the minimum volume ellipsoid that is enclosing, right? In this case, we are finding the minimum volume ellipsoid that is enclosing, and in this case, we are finding an ellipsoid for which 1 by radius, sum of 1 by radius is the maximum possible. So in other words, if there is a radius which is very small, this quantity will become very large, and therefore we are trying to make sure that at least one of the radius becomes very small, right? So different kinds of objectives are there, and all of them are basically working on the shape of the ellipsoid. In some way they are affecting the shape of the ellipsoid that is enclosing, right? So that is the interpretation for the optimum experiment design problem in the linear case. Now we have only studied the linear case. The advantage of the linear case was that our objective function, which was in terms of the covariance matrix, the covariance matrix did not depend on the actual x. So we did not actually need to know what the measurement revealed or what the estimates are. We can just do this design in advance. Just if we know the model, we can do this design and only deploy the sensors at the locations that are required. That is generally not true. If you don't have a linear model, if you have a non-linear model, then you may actually have to do the measurements and then based on that infer which are the locations and then redeploy accordingly. So a linear model has the advantage that you don't actually need to do the measurements. The covariance matrix is independent of x, so we can just design the covariance matrix before doing any single measurement. So that was all about the optimum experiment design problem.